Hello everybody, in this video we're going to start piecing together how light is going to interact with atoms. This is going to get a little bit crazy, so hold on, because now for the first time in astronomy we're not going to be talking about the very, very big, we're going to be talking about the incredibly small. Because for us to understand how light interacts with matter, we need to go ahead and delve into the quantum realm. We need to understand light as a particle, and we need to understand the atom. All right, so let's go ahead and get ready for this and jump right in. What we want to know is we want to be able to explain why we see those emission lines and those absorption lines at very specific wavelengths. It has to do something with the interaction between light and matter. Whenever I'm saying matter here, I'm talking about matter on the atomic or molecular level. So really what we want to answer is the question of how do these two things interact? Here we have an incoming light particle, has a certain wavelength, that has a certain energy as we're about to see, and then it's going to encounter, say, an atom, which has a nucleus, and then these electrons that orbit at very specific distances, so at set energies. So what happens when these two meet? And that's going to be the question that we're going to be working on for quite a while. But to understand this, we need to understand light as a photon, a particle of light, and we need to understand the atom, or at least a 100-year-old model of the atom, the so-called Bohr model of the atom, which gets the energies that the electrons have correct. Okay, so back to motivation. We saw, whenever we looked at, say, the emission spectrum of hydrogen or the emission spectrum of helium, we see these emission lines at very, very precise wavelengths. The same is true for absorption lines. So if we're talking about emission and absorption lines collectively, we usually just call those spectral lines, because they're a line in a spectrum. But they occur at very specific wavelengths. What is it that's restricting them to, say, this red versus this red? Why can't helium make this red over here? Why can't hydrogen make this yellow? What is physically restricting these wavelengths to very specific values, very specific colors? And for this, yes, we have to go into the quantum realm. We have to understand light not as a wave, but as a particle. And the fundamental bit of light, this is one of the elementary particles in the standard model of particle physics. The particle of light is called a photon. And we're going to talk about how that photon, as a particle, interacts with another type of particle, an atom, made up of protons, neutrons, and electrons. And here we're going to adopt the 100-year-old view of the model, the Bohr model of the atom, because it's going to get all the electron energies correct. But at the very end, I'm going to try to give you a more modern perspective on what our current view of the atom is. It's going to be a little bit beyond the scope of this course, but hopefully I would be remiss in my duties if I did not give you the modern view of what an atom is. Okay, so light as a photon, light as a particle allows us to do something pretty amazing. And for this, I really hope you've gone through some of the slides already. Otherwise, this might be moving a little bit quickly. I'm assuming that you have reviewed the slides so that I can jump right into the energy of a photon. Because a particle of light, the smallest little bit of light we can consider, has a very set energy. And hang on one second, I'm going to turn on the lights here. I need to get some more photons running around in this room. Okay, thank you for that brief aside. But light as a particle, a photon, has a very set amount of energy. So you have this photon. That photon has a distinct, unique value of energy. And every photon that's just like that photon has the exact same energy. What determines the energy of that photon? The wavelength of light. So this is where we get to see the wave nature and the particle nature combine. So If we say we're talking about red light, and let's just choose a wavelength of red that's associated with a hydrogen atom of 656.3 nanometers. That's this beautiful color of red right here. So if you have a photon that has a wavelength of 656.3 nanometers, then it has a very, very set energy. If you want more of that red color, you need to add another photon. So that's how you're going to make things brighter. You can't just amp up how bright a photon is. A photon has a very set amount of energy. To make something brighter, you need to add more photons of that wavelength, of that energy. I know, it's a little bit weird. So every photon out there has an associated wavelength, and that wavelength determines that photon's energy. And it can't be any different. You can't have a red photon, a photon that is associated with the color red, with a very specific wavelength of, say, 656.3 nanometers, a very specific red. You cannot have that photon have a range of energies. It has to have a set energy. Okay, whenever you are restricting things to certain values, whenever you're restricting something to a certain quantity, we say things are quantized. So essentially I'm saying all of this to say that photon energies are quantized. Photons themselves are quantized, restricted to certain values. And that idea of quantized, that is where the term quantum mechanics comes from. That things come in discrete packets of energy, in this case when we're talking about the photon. What is the energy of the photon? Well, the energy, measured in something called the electron volt. So the electron volt is just a unit of energy. If you're curious about what the electron volt is, it is the amount of energy gained if you take an electron and you move it through an electric potential of 1 volt. So it literally is an electron volt. So the electron volt, usually EV, is just some amount of energy. I know you're probably not used to units of energy much at all, but the SI unit for energy is joule. Another unit of energy that you might be more familiar with is the calorie. Really, whenever you read something on the food, that's the kilocalorie. But it's just some measurement of energy. Let's not worry too much about that, other than you always have to use the right units for the equation you want. So if you want the energy of a photon in electron volts, then it equals some number, 1240, divided by the wavelength, but you need to put that wavelength in nanometers. So this version of the equation assumes that the energy is in electron volts, and it assumes that your wavelength is in nanometers. If you change either of those, you need a different equation. Okay, now I'm not going to have you memorize equations. I have you run through some use of this equation on homework and things like that, but not on quizzes or exams. What you want to remember for quizzes and exams is that the energy of a photon is inversely proportional to the wavelength. I make the value of the wavelength larger. The energy, I'm dividing by a bigger number, so the energy gets smaller. So longer wavelength light has smaller energies. Smaller wavelength light has larger energies. Okay, now how is this useful? Well, if we know the wavelength, we can solve for the energy of that photon, because now we can see that talking about wavelength and the energy of a photon are synonymous. So let's take this beautiful color of red right here, has a wavelength of 656.3 nanometers. What is the energy of a single photon of that red color? Well, let me just use my handy dandy equation. Energy equals 1,240 divided by the wavelength. Plug that in, calculate that with a calculator. 1.89 electron volts. So every time you see this color of red that has a wavelength of 656.3 nanometers, you have a bunch of photons entering your eye that all have energy of 1.89 electron volts per photon. Another useful thing, and notice I have these in green, so again, don't memorize these for quizzes and exams, but you will interact with it on the homework. I could know the energy, like maybe there is some physics out there that lets me predict that there should be this energy. And then I could solve for the wavelength to actually, design an experiment to check to see if my prediction is correct, if I can actually predict the energies. So let's take an energy now of 10.2 electron volts, just a number, not chosen at random. So if I have a photon that has 10.2 electron volts of energy, that's a bigger number, so bigger energy, smaller wavelength. I know my wavelength is going to be smaller than 656.3. But I can go ahead and rearrange the equation. Lambda equals 1240 divided by the energy, plug in the energy, put that into my calculator. Oh. So a photon that has an energy of 10.2 electron volts has a wavelength of 121.6 nanometers. That's in the ultraviolet part of the electromagnetic spectrum. So that's an ultraviolet photon. So notice that ultraviolet photons have more energy than visible light photons. That might be why you don't want to be exposing yourself to a lot of ultraviolet light. Every photon is carrying a pretty large amount of energy, enough energy where it can actually break the molecular bonds in your body, in your DNA, in your skin to cause damage. Okay, so now we can revisit our electromagnetic spectrum. We have sorted the electromagnetic spectrum by wavelength and equivalently by frequency. Now let's sort it by energy. So let's go ahead. We have our radio waves are the longest wavelengths. Our gamma rays are our shortest wavelengths. And let's go through this a little bit logically. Radio waves, the biggest wavelengths, the longest wavelengths, will have the smallest energy because energy is inversely proportional to wavelength. So radio waves have the lowest energy per photon, which is why we're pretty safe having radio waves be our form of communication. They have very low energy per photon. Shorter wavelengths are gamma rays, our shortest wavelengths. Short wavelength, super large energy, have the highest energy. So gamma rays have the highest energy. And the shortest gamma rays out there produced naturally in the universe can have energies equivalent to, like one gamma ray can have an energy equivalent to a Major League Baseball player throwing a baseball at you at 100 miles per hour. That's about as high as we can naturally produce for a single photon, but that's a lot of energy per photon. You don't want to be exposed to gamma ray radiation, gamma ray light. It's not good for anybody. In fact, a term, we could flood this room or the earth in gamma ray light, and I think the term that we'd use then is sterilization. It would kill all life. So let's not mess with gamma rays. All right, so now we understand energy connects to the wavelength of light. So if we're talking about a photon of light, for a given wavelength, there's a very specific energy. And every photon of that wavelength has that very specific energy. Or to think about it more appropriately, every photon has a set energy, and that set energy tells you the wavelength of that light. So that's one half. We now have our photon coming in to interact with an atom. How are we going to think about atoms in this class? Well, we are going to use a model that was developed in 1913, the so-called Bohr model of the atom, which is probably the atom that you've learned about if you can remember back to middle school and high school. So we will use the Bohr model of the atom. And the big thing about this is Bohr is going to quantize the atom. I'm going to come back to that. Remember that quantized means restricted to a certain number of states, a certain number of values, very restricted to certain quantities. There are no in-betweens, it's this or that, not between this and that. So things are restricted to very specific quantities. Okay, we're going to come back to the quantization of the atom, which is really what Bohr did about 100 years ago. But let's actually talk about what the atomic structure is in the Bohr model. And yes, this is a throwback to our middle school science class, where what is an atom? Well, you always see diagrams like this. You have the nucleus in the center of the atom, which is the nucleus is made up of protons and neutrons, which we now know protons and neutrons can be busted down into quarks. So they're not fundamental bits. But we have our nucleus that's made up of protons and neutrons. And then you always draw electrons orbiting around the nucleus. So you have protons and neutrons making up the nucleus. Then orbiting the nucleus, you have electrons. Protons have a positive charge. Electrons have a negative charge. And neutrons have no charge at all. And remember, opposite charges attract. So protons and electrons, a positive charge and a negative charge, they want to attract towards one another. There is an attractive force between them. Very similar to gravity, except it's the electromagnetic force, the Coulomb force to be specific. Similar charges, so a proton and a proton, two positive charges will repel one another. Two negative charges, an electron and electron, will repel one another. So you need opposite charges for them to be attractive. The electromagnetic force, unlike the gravitational force, is both attractive and repulsive. The gravitational force was only attractive. Okay, so now we have the protons and the neutrons making up the nucleus, and then we have electrons orbiting the nucleus. Let's take a look at the electrons and how they're orbiting. Okay, so first, let's just go to the fact that we have our positively charged nucleus, which is going to be represented by the big ball right here. And then we're going to have our electrons. So positive charge, negative charge. So if I want to move them away from one another, if I want to pull this is getting, the negative charge is getting pulled towards the positive charge. There's a force trying to bring them together. So if I want to keep them separate, I have to pull them apart. I have to exert some energy to move the electron away from the nucleus. Kind of like if the Earth weren't moving, it would fall into the sun. And if I wanted to move an object away from the sun, I'd have to give it energy to move it further and further away from the sun. Or I'd have to give this ball energy to throw it up into the air, to move it away from the gravity of the Earth. So to move the electron away from the nucleus requires some energy. How did we get a planet to orbit around? Well, we just gave it some orbital velocity, right? And that orbital velocity balanced out the gravity pulling it in with the rotational energy of it moving around and around and around. Let's do something similar with our Bohr model, because the electron is attracted to the nucleus. So let's set it in motion. Let's put it in orbit around the nucleus. And this is why we draw our electrons in orbit around the nucleus. They orbit it. Except it's not like gravity. The electrons can't orbit, say, at this distance, where I could calculate the orbital velocity based on the distance, and then it could be this distance, this distance, this distance, this distance, this distance, this distance. Can't be any distance. Electrons are only allowed to orbit at specific distances, say this distance and this distance. It can't orbit at any distance in between. How it can orbit is restricted to certain values. Where the electron is allowed to be to orbit is quantized, restricted to a certain value. So here I have, say, one place where one distance away that the electron can orbit. If I wanted to move it to a further distance, that takes energy, right? So one way to think about it is, instead of thinking about it in restricted to certain distances, is restricted to specific energies. And that is going to be the genius of Bohr, that the electrons can't orbit at any distance. They can only orbit at specific distances. To say that another way, exactly the same, is that electrons can only orbit at very specific energies. And these electron energies, since they're very, very specific, restricted in values, are quantized. The Bohr atom is quantized. There are no in-between energy levels. It orbits here, at this distance, or it orbits at this distance, or maybe some more distances further away, but we'll just use 2 right now. It can't orbit in between those 2 distances. I know, quantum mechanics is weird. We're not even really to the big part of the atom yet. Okay, so each allowable electron energy, every place it can orbit, we call that an electron energy level. And there's only a set amount of them, right? Since it can only orbit at specific distances, there are set energies the electron can have, and each one of those we refer to as an electron energy level. So this distance right here, this inner distance, would be 1 electron energy level. This distance right here would be another electron energy level. A third distance further away would be the 3rd energy level, then the 4th, 5th, 6th, so on and so forth, to however many there are. And that electron can only have those energies. The energies associated with this energy level, the energies associated with this energy level, it cannot have an energy in between. That's the weird part, and just sort of have to swallow that bitter pill of reality, that that's how things are. Electron orbits are quantized. They are restricted to specific energies. Okay, that's where we're going to pick up next time, that we have energy levels and they're restricted to certain values of energy. The electrons can only have specific energies, kind of like a photon can only have specific energies. Maybe we can get those two to get along somehow and match electron energy levels to photon energy levels. And if there's a match, then we have interaction. That's going to be the trick. However, as I said, I would be remiss in my duties if I did not push past the Bohr model and talk about what the modern view of an atom is. Because these orbits do not exist. A little ball of an electron, this green ball with a minus sign, that's not what an electron is. So, what is the modern view? And this is a lot of green text. So, if you want to check out, stop the video. If you're curious about what the modern view of the atom is, the so-called electron cloud model or the quantum mechanical model, then keep listening. It's a little bit of a wild ride. So, electrons, just like photons, just like everything in the quantum mechanical world, are waves. They're also particles. The weird part is that electrons are particles with mass, while photons are particles without mass. But either way, an electron is described as a wave in the modern view. And that wave gives us a probability of where it's going to be located around the nucleus. And that probability is given by Schrodinger's wave equation, which allows us to define a cloud, let's go with this picture down here, around, say, our nucleus, of where the electron is allowed to be. And it gives us a probability that you'll find it, say, there's a probability that the electron will be here versus the electron will be here versus it'll be here versus it'll be here. There's a certain set probability that you will find it at a certain location around the nucleus. Weird. So the electron is sort of like just this wave that is governed by this wave equation that Schrödinger came up with that gives you the probability of where it's going to be located. So in that view, the electron is sort of distributed everywhere into this cloud around the nucleus. You can find it, but the more you know about its position, the less you know about how it's moving. The more you know about how it's moving, how fast it's moving, the less you know about its position. That's called the Heisenberg uncertainty principle, and it's weird. Quantum mechanics is weird. Okay, so the electron is smeared out into these probability clouds around the nucleus. We call each one of these probability clouds an orbital shell. Now, if you remember from your high school chemistry, you might remember, because this is how we're going to make sense of the periodic table. This is what gives us the modern design of the periodic table and gives a rhyme and reason to it, that each orbital shell has an associated letter, a S, P, D, or F shell. And notice that they get increasingly complex in their shapes as you go from an s orbital to a p orbital to a d orbital to an f orbital. And there are higher level orbitals as well. And you just keep on going through the alphabet. But these are the primary ones. So, what makes an orbital an orbital? So each electron, each orbital shell, for an electron to be there, it has a set of unique, what we call quantum numbers. And those quantum numbers are what we call n, l, and m sub l. N describes the electron's energy, L describes its angular momentum, and m sub L describes its magnetic quantum number. Let's not worry about what all of those things are. We're safe just saying quantum mechanics is weird and hard. Talk to any physicist, and if they say quantum mechanics is easy to understand, they're lying to you or to themselves or both. It's weird, it's difficult. But we have these quantum numbers that describe the energy, that's important, the angular momentum, and the magnetic component. And then within each one of these orbitals, we can stuff with each one of these electron clouds, we can stuff 2 electrons. According to the electrons, another quantum number, its spin number, its quantum spin number, m sub s, which is going to be either plus 1/2 or minus 1/2. And if you remember your Pauli exclusion principle, if you're looking at a p orbital, you had 3 little places, and then you could put an up arrow and you'd fill all the ups, and then once you filled up all the ups of the p orbital, then you could put the down electrons in as well. And you couldn't have 2 ups or 2 downs in the same orbital. I know, insane, but this is shown through endless number of experiments to be representative of reality with crazy powerful predictive power that gives us things like the ability to watch this video on a computer that works based on these principles of quantum mechanics. Okay, so now we know that we have these orbitals, you can stuff electrons into them, and it's all really, these regions are just volumes that describe where an electron can be with a certain probability. It's almost as if the electron is distributed in this probabilistic cloud. Let's call this electron cloud model. And all of that is really, really difficult. And I know I'm not doing it nearly enough justice because you have to take pretty much an entire class to start really getting all of this and to break everything down. But the thing about this is the energies that the electron has in each one of these, say, angular momentum equals 0, that's an s orbital, angular momentum equals 1, that's a p orbital. Each one of, or the energies that the electrons can have match the energies that are described by the Bohr model. And what we're after for this interaction between light and matter, or at least for the purposes of this class, is the energies of the electron matching the energies of a photon. So why don't we just use the simple Bohr model if it's going to get the thing that we want, the energies, correct? Which is why we're going to use the Bohr model in this class instead of this awesome, mind-blowing electron cloud model. All right, thank you for tuning in. Hopefully you stuck around for the extra little bit and you have a little bit of an appreciation that quantum mechanics is weird, atoms are awesome. All right, see you in the next video.